Great. So last class we have started with the inductors. Let's go ahead. Yeah, so I'm having issues with the mic and I hope everyone's able to hear me, right? Great. Then, so just to brief it up, last class we did flux is equal to Li. E is minus d phi by dt, where you got this back EMF. Hope everyone has gone through this. Then we defined self-inductance of a solenoid, mu naught n square pi r square L. Then we defined energy stored and the magnetic energy density. So with this, we'll be checking out. Let's see. So let's say if you have an inductor with a battery. So we have seen what happens if we keep a capacitor with a battery, resistor with a battery, and we'll see with an inductor. Now, so if you keep a battery at t is equal to 0, find the current at time t. So if you just connect an inductor with a battery and if you leave it, what will happen to the current at time t? This is 10 Henry, this is 2 Farad. This is 2 ohms and this is 3 volt. This is A, this is B, this is plus Q, this is minus Q. Let's say Q is equal to T square by 2. B is a pretty good one. You can see all the 4 elements that we studied: battery, capacitor, inductor, resistor. Find VA minus VB at T is equal to 2 seconds. Understand, Kirchhoff's law doesn't care whether you put a battery, resistor, inductor. Kirchhoff's law is still valid. Got an answer? Chat box co-host. You know the standard stuff. So let's see. I'm not keeping that great, but let's see. We might wrap up a little early today. Who knows? I might feel better and we might continue also. So I should not give you any hopes. Right, Purvada? Right, Niharika. The second is a good one. So when you have an inductor, you can replace that with a battery of LdI by dt. Apply Kirchhoff's law. V minus LdI by dt is equal to 0. So di is equal to V by L dt. 0 to I, 0 to t. I is equal to Vt by L. So straightforward. So in an inductor, if you put a battery, the current will just keep on piling up. It never decreases. What about this guy? 15. I don't know the answer. Let's see, anyone else got. You have Purvaja got 15. Anyone else got 15? What is the potential difference between A and B in 2 seconds? Just to give an idea, how will the current flow? Current is flowing from right to left. How do you know that? Plus Q is positive charge and Q is increasing. dq by dt is current. So current is going from right to left. How much is current? I is equal to dq by dt, which is 2t, t. So at t is equal to 2 seconds, charge is 2 coulombs, current is also 2 amperes. Now apply Kirchhoff's law from A to B. So VA, you are going in the battery from negative to positive terminal, plus 3. You are going in the direction of the current, minus IR. Then you are going from positive to negative plate, minus Q by C. Then you are going through an inductor, minus L di by dt. Like I said, if nothing is mentioned, assume always the inductor is opposing. The signs will take care of it. This will reach VB. So this is VA plus 3, current is 2, resistance is 2, charge is also 2, farad is 2, this is 10, di by dt is 1. Plus 3, minus 4, minus 1, minus 10. VA minus VB will be 12. Right, Porojan, you changed it. You got it. Please check the signs. There, that's what makes this problem really good. You have all the elements. This is not a steady state. Charge is changing, current is changing. Kirchhoff's law is always valid. Kirchhoff's law doesn't care what element you keep at what time, because what it simply says is the potential differences. Some of the potential differences must be VA minus VB. Clear with this? Let me ask you one more easy one on this. Let's say we have a solenoid. Length L, radius R, N is the number of turns per unit length. You took this, you have rewound it to radius R by 2. Find ratio of self-inductance. Energy stored. Energy density. I can ask you more questions. Magnetic moment. But we have done that before already, I guess. Magnetic moment and one more. Magnetic field. For same current, huh? Get these three. This is the third time you're seeing this reminding stuff. Second time, I guess. So find the ratio of self-inductance, ratio of the energy stored for the same current. Find the ratio of energy density. Hope you remember what is energy density, energy per unit volume. Yeah, this is a decent mains level question. Let's see. 1:2. Anyone else? 30 seconds more. Let's see. What is self-inductance? L is equal to mu naught. First of all, when you take n turns, what happens? Remember, small n remains same. So this length becomes 12. N will remain same. This we had a discussion. The total number of turns will double in this thing. So what is the magnetic field? Magnetic field is mu naught Ni. So this is constant. They have same magnetic field. So self-inductance L is equal to mu naught constant, N square constant, pi constant, R square. Yeah, this gets messed up. This messes up. So L is proportional to R square L. So L1 by L2 will be R square L by R square by 4. Length is double. 2:1. What is energy stored? Energy is half Li square. This is also proportional to L. E1 by E2 is 1:1. No, 2:1. What is energy density? dE by dV is 1 by 2 mu naught B square. This is constant because B is constant. 1:1. Right, Puroja. But I think you got reverse, or maybe you found final minus initial. Final by initial. All got this? Easy question, but most people goof up because they don't remember the inductance ka formula. So do remember that. Let's see a question. Let's say we have a solenoid. Number of turns per unit length. R is the radius. We have a metal rod which is entering inside. This speed is V. Mu of iron is nothing but mu relative into mu naught. So don't worry about that. That value is given. Mu iron is given. At the same time, current I is flowing in the inductor. I is equal to T. T is time. So the total length is L. So at T0, the rod is about to enter. Find the potential difference across the solenoid at time T. This is a good one. If you know what you're doing, it is easy to solve, but it's a good one. Even at an advanced level, this is a decent question. So you're messing up the current and the rod is also entering. Let's see how you handle this. Try, you got 2 minutes. How do we start? So let's say when it is entering inside, let this be x inside. Then this will be L minus x. So what is the self-inductance? So you can divide the self-inductance into two parts. You have two solenoids, one with vacuum and one with a metal. So what is the formula? Mu naught n square pi r square length of the rod, which is L minus x. So this is the solenoid in vacuum, plus mu medium n square pi r square x. What is x? Vt. There you got the solenoid. So what is flux? Li. People figure out this much also. This is where they goof up. Then they write EMF is equal to L dI by dt. EMF is minus d phi by dt. This is minus L di by dt minus I dl by dt. Bas. That's it. This one thing makes the whole thing tricky. Because whenever you ask someone solenoid, there's L di by dt. L di by dt. Matlab, it becomes like a flow. It's like asking F is equal to ma, which is a blunder. If m is constant, then F is ma. If L is constant, then it is L di by dt. Here, L itself is getting messed up. Clear with this? So that's what I was saying. It is easy to solve, but you should realize, boss, L is changing. I can't use L di by dt. That's it. There's nothing big deal about the question other than that. Clear? Next thing. Let's see how they'll ask a proper advanced question. This next one is a pretty good one. Could be an advanced paragraph or a matrix matching. And you will see why. Same thing. Do you remember we have done this question with resistor and capacitor? Now we are putting an inductor. So we have an inductor, we have gravity, vertical smooth rails. There is a magnetic field B here. Mass of the rod is M. Length of the rod M and released from rest. Describe the motion. And find the position at time t. So assume it is starting from here. You can take this as x is equal to 0. So if it goes down, take x as positive downward. Find position at time t. Or displacement from the at time t, same thing. Let's get this. So this thing, right, with the resistor, capacitor, inductor, these three models are pretty important. And among these three, this thing is even interesting. Try. I'll give you 2-3 minutes. First figure out what is happening and then everything will fall in place. Hope the picture was clear. Anyone confused with the picture, please ask. This is the front view, so gravity is pulling the rod down. Anyone figured out? It's your favorite motion. What is our favorite motion? SHM. This rod starts oscillating in SHM. Didn't I tell you? SHM will keep haunting you till the end. Again, but remember how we wrote the steps in resistance and capacitor. The steps will be the same. See, let's say after time t, you have gained velocity v. If you're going with velocity v, motional EMF, it will act like a battery. Because of this, you get a current I. So EMF will be BLV. Current I will be BLV by R. Sorry, there is no R. BLV. That means this circuit will look like we have an inductor and we have a battery. This is L, and this is BLV. And this is current I. So BLV minus LdI by dt is equal to 0. So we got di by dt is equal to BLV by capital L. Now take the FBD of the rod. So in these questions, right, this is the logic every time. You write one equation, Kirchhoff's loop, and one force equation. Now we have a current carrying rod in the presence of a magnetic field. This will create a magnetic force ILB and mg downward. Because of this, you'll have an acceleration. You'll have mg minus ILB is equal to ma. Now you can clearly see here, I have di by dt here, but there is only I here. So differentiate it to get di by dt. Differentiate with respect to time. Mg will become 0. This will become LB di by dt. This is m into dA by dt. Acceleration is nothing but dV by dt. This will be LB, BL, V by L. This is m into d square V by dt square. So we get d square V by dt square is equal to minus b square L square by ml into V. This is your omega square. And that's your SHM. So the equation will look like V is equal to V naught sine omega t plus phi. This is your general solution when you get an equation like this. Now we need to find V naught and phi. Omega to we know. Once I know V naught and phi, then I can integrate again and I can get X. So in this question, I can ask you multiple things. Find the maximum distance it will go down. Find the time period of oscillation. Find the maximum speed. Getting it? Find the velocity. I can ask you everything. Now, can you try from here? Try. I'll give you another minute. I got everything. How do you find V naught and phi? Have a look at the steps and the equations. So this and this. Yeah, once you got the equations, your job's done actually. How do we get? Look at the initial conditions. At t0, your velocity is 0 and acceleration was g, isn't it? A is g because initially current was 0. So there is only one force mg. So initially acceleration was g. So V is equal to V naught sine omega t plus phi. So when you put t 0, should you get so phi is 0. Acceleration is dv by dt, which is V naught omega cos omega t. At t is 0, we'll get G is equal to V naught omega. V naught is equal to G by omega. There. So you got velocity V is equal to G by omega sine omega t. And your position x will be G by omega square 1 minus cos omega t. So if you actually look at this motion, tell me one thing. During SHM, at which point you have zero velocity? Extreme position. So x is equal to 0 is actually your extreme position. You're leaving the particle from extreme. Then it will go somewhere here, x is equal to a. It won't stop there, it will go to the other extreme. So this would be the maximum distance it will travel. This is another extreme position. This is your mean position. And amplitude is how much? Amplitude is G by omega square. So this rod will keep moving between 0 to 2a. That is the maximum distance it will go down before taking a turn. Clear with this? So the current in the inductor, right? If you see, when it is coming down, current is going in the inductor, and then current comes out of the inductor. So the inductor is taking current, giving current, taking current, giving current. So if you see, a conductor does not dissipate energy, so the energy can't go anywhere. The rod will just keep oscillating. So energy goes from gravitational potential energy to magnetic energy in the inductor and so on. It keeps oscillating between these two. Clear with this? Good one. So there we have three models in this: a resistor, a capacitor, and an inductor. Next one. We have a solid, infinite solid cylinder. Carrying current I. Radius R. Find a ratio. Now remember, in magnetic energy density, we said magnetic field is nothing but another form of energy. So if magnetic field is another form of energy, find the ratio of energy stored from x is equal to 0 to x is equal to r. Basically, this is the inside. And x is equal to r to x is equal to 2r outside. Get me the ratio of the energy stored. So how much energy will be there inside the inductor, inside that solid cylinder, and how much energy will be there from R to 2R? Do you guys remember we have done something like this in capacitors? ये क्वेश्चन था. A charged hollow sphere is there. Find the ratio of energy stored from R to 2R and 2R to infinity. याद आया energy density का? This is the magnetic energy density. For first, you need to remember the formulas for a field inside a solid cylinder and outside the solid cylinder. Anyone remembers? Even if you don't remember, you know how to derive using Ampere's law. First get the field. Get the field inside and outside. In case you forgot, this is how you do. But try. Let's see. Question is this. And we have to use energy density. So I'll just write down the field in case you don't remember. So this will be mu naught I by small r by 2 pi r square. Outside is easy. It just behaves like a wire at the thing. This is for r less than r and r greater than r. And we know the energy density is energy by volume, dE by dV is 1 by 2 mu naught b square. So the headache is how will you choose the element? So here we take an element like a thin cylinder because the field lines are changing with small r. So this will be your element. Let this be smaller. Let the thickness be dr and let the length be L. So what is the volume for this thin element? Surface area, which is 2 pi r into L. That is your surface area into thickness. Great. So you want energy from 0 to r. So the formula is integral 1 by 2 mu naught b square, which will be mu naught I small r by 2 pi r square ka whole square into volume will be 2 pi r L dr. This will go from 0 to r by energy from r to 2r. B changes. Mu naught I by 2 pi small r ka whole square 2 pi r L dr. So if you see 2 mu naught will cancel, mu naught I will cancel, 2 pi will cancel, 2 pi L will cancel. You will be left with r cube dr r power 4 by dr by r by 2r. That will be r power 4 by 4. That will be 1 by 4. This will be ln 2. No? Denominator will get ln. That is here there is an r square here and there is an r here. One r will cancel. You got dr by r left. Check. I hope that is right. So I could have asked you to find the energy stored outside for a given length and all that. So yeah, you would have got it. There. So you should know the field due to the solid cylinder and then use energy density and then solve. Any doubts on this? Yeah. Next thing. LR circuits. So just like we have RC circuits in LR circuits. So let's say we have an inductor L and we have current I. We know an inductor, the back EMF, again assuming L is constant, E is L dI by dt. Now you need to understand exactly what does an inductor want. See, inductor does not have a problem with current. You can send how much ever current you want. What inductor doesn't like is change in current. So an inductor opposes the change in current. That means if you try to change the current, it will always try to maintain the current somehow. If there is a possibility, it will try to maintain. Similarly, if you think about capacitors, what do capacitors do then? Capacitors oppose the change in voltage. Think about it. Initially, the moment you close the switch, right, it will let the current pass. Initially, voltage was zero. It will not try to charge only. Eventually, at infinity, what will happen? It will not let the current come because once it is full, it doesn't want the voltage to change anymore. So this thing opposes the change in voltage or charge. Same thing because Q is equal to CV, both are related. That means a capacitor, it will try to maintain the charge. It will try, matlab, it will discharge, but at that instant, it will have the same charge. It takes time to discharge. So if you take an inductor and if you take a battery with a switch, and if you close it at T0, sorry. At T0, look at this. The moment you close the switch, current will try to flow through the inductor. Inductor will say, boss, I don't want any current. So it will try to behave like an open circuit. If you remember, a capacitor does the reverse. A capacitor at T0 will behave like a wire. Since there's nothing to oppose, charge will just pass through it. At T infinity, which is your steady state, eventually the current will become constant and inductor is okay with that. It will behave like a wire. At T infinity, a capacitor will be fully charged. It won't let any charge flow. It will become open circuit. So be careful. Both are opposite. So a capacitor and inductor will have the reverse, the steady state. Clear? Let's see a question. Hope you remember this. Same question with capacitors. The switch is closed at T0. Find the current at T0 and T infinity. Same story. Find the current in this branch at T0 and T infinity. Fine. Let's see the first one. At T0, inductors will act like open circuits. This is how the circuit will become. All will be in series. At T infinity, they'll become wires. They'll become parallel. V becomes R by 3. So current actually becomes 9 times. What about this guy? At T0, inductor becomes open. So all the current will just go through the 2R. V by 3R. At T infinity, it becomes a wire. These two are in parallel. 2R by 3 plus R. R equivalent will be 5R by 3. So in this branch, the current I will be 3V by 5R. I didn't ask you that. 2R and R are in parallel. So the current will split in the ratio of 1:3. I by 3 and 2I by 3. Therefore, the current I will be V by 5R. Clear? Be careful. What you 3V by 5R is the total current. That is, I'm not asking you that. Question was current in the 2R ka branch. You have to split the current again. Clear with this? So these things will look like same thing like capacitor ka things. So that is okay. Easy stuff. But if they really want to ask you something good on this, in steady state, this is how you play. You put an inductor, capacitor, resistor, battery, every damn thing. Let's do this. Go through the question, take a minute, and then I'll explain you a few things and then we'll go ahead. Yeah, wires are connected in the middle. And if they're not connected, they will show like this. So don't worry. These things are connected here. Let's see. I'll explain the question a bit. नीचे आंसर दिया रे गॉड Someone's typing wrong answer. See what is happening. So initially it was closed for long time. So you closed it for long time. If you close it for long time, what will happen to the inductors? They become wires. What will happen to the capacitors? They become open circuit. And remember, this is an ideal voltmeter. An ideal voltmeter will have infinite resistance. So there'll be no current in this branch anyway. So look at eventually what happens. Capacitor becomes open. Capacitor becomes open. Inductor becomes a wire. Inductor becomes a wire. Sorry, inductor becomes a wire. So if you look at the current, it will go like this. It will go like this. It can't go this way because you can't go here, you can't go here. So there's no current in the 4R branch. You'll go like this, you will go like this, and so current is only flowing in this triangle. So both the inductors will have current. Now what you did, you suddenly opened the switch. And I told you, if you suddenly open the switch, what will the inductors try to do? The inductors will try to maintain the current. Capacitors will try to maintain the charge. The currents will not become zero. So something happens. This current will start flowing in some weird way. Now think, I'll give you 2 minutes. See if you can figure out something. So let me help you out a bit. Close the switch. Can you find the current in the inductors and charge in the capacitors? Let's start from there. Close the switch for a long time. Find the current in the inductors, find the charge in the capacitors. Let's start from there. Get that one. I'll give you a minute for that. And then we will open the switch and then we'll see what to do. So in this kind of question, the catch was this. When the switch is open, the inductors will maintain the current. Capacitors try to maintain the charge. For that instant, just after opening the switch. If you give some time, then the charges, current, everything will start getting messed up. We are not going to do that. That is after time t, we will not do. Just after opening, what was happening? That is what he asked. First, find the currents and the charges on the capacitor when the switch is closed for a long time. Let's see. You just have to carefully draw the pictures. So you close the switch for a long time. So the current will flow like this. Current will flow like this. Current will continue here. Current will continue here, and current will come back here. Right. And remember, this is an ideal voltmeter, so R is infinity. So you can just remove this voltmeter here. So this becomes a wire. Now see, this capacitors, right? Let the charge be Q1. This is minus Q1. This is Q2. This is minus Q2. We don't know the charges. This inductor becomes a wire. Let the current be I. This inductor becomes a wire. Let this current be I and I. Clear with this? Because see, you can't have a current here. So in this current, it will be 0. Agreed? Because if the current can't go here, because the 2C capacitor won't let the current flow, and ऊपर तो नहीं जा सकते because voltmeter won't let the current flow. You are done. So what is I here? I is nothing but V by R. There is only one resistor. And what about this capacitor? Apply Kirchhoff's law. Take this loop and take this loop. So if you go in this loop, you will get nothing. There is no voltage there. So you'll get small I into 4R minus Q1 by 2C is equal to 0. But I is 0. Q1 is 0. If I go here, you'll get E naught minus Q2 by C is equal to 0. Q2 is equal to C E naught. So the 2C capacitor is empty and this C capacitor will have a charge of CB. Clear till here? This is the steady state. Now you want to open the switch. So now if you open the switch, so this was 0, this was 0, this was CE naught, and this was minus CE. Now see what happens. Now if you suddenly open the switch, this here switch is closed. Now if you open the switch, something weird happens. This current which is flowing, so this inductor mein current I is flowing, this current I is flowing, this current I is flowing. Now this inductor will do, instead of previously it used to send the current into the battery, now this current will start driving into this capacitor. Current will go like this, current I will go like this, and like this. Basically, it will make an 8 shape. See, inductors don't have a problem with the current, right? So they will try to maintain the current. Now you need an alternative route. The moment you open the switch, you can't go through the battery, then it will try to push through the current, push through the capacitors. Make sense? Capacitors will let the current flow. They don't have a problem. If the current is coming, they will take their current and they'll start charging. But at that instant, they will still have the same charge, CE. This is what will happen to the current. Current will start flowing like this in an 8 shape. Is that making sense, everyone? So instead of going through the thing, your switch is open. So instead of going through the battery, it will divert the current. So this was 0, and this was CE, and this was minus CE. So what do you want to find now? Let's see the question now. You want the potential difference between P and Q. P is here, Q is here. So let's go in this loop. VP, you're going opposite to 4R, my plus I 4R. You're going with IR, minus IR is equal to VQ. So VP minus VQ is equal to minus 3 IR. This will be nothing but 3 E naught. E naught is nothing but 4 volts, minus 12 volts. Clear? The voltmeter will show 12 volt ka reading. Any doubts on this? Second part of the question. Find the heat produced in the 4R resistor. So if you leave the circuit like this, eventually, right, all the currents will become zero, all the capacitors will become zero. This is the situation right now. If you leave it like this, eventually, because of the resistors, they will dissipate, and in the way, nothing will be left. Everything gets dissipated. So after a long time, all currents and charges become zero. Meaning the entire system energy becomes zero. So where does this energy go actually? All this energy becomes heat, isn't it? So what was the total energy just after the switch was open? The total energy just after switch is open, we have two capacitors and two inductors. So the energy will be half Li square plus half 2Li square plus half CV square. The other capacitor is zero. Why isn't the current going into C initially? Which current you're talking about, Poroja? Where? 2C or C? Which one you're talking?
C.
Initially बोल रहे मतलब steady state है ना?
हाँ
If you close the switch for
मतलब स्विच ओपन करने के बाद इनिशियली
किया ना, ओपन करने के बाद जा रहे हैं ना करंट ये. This current, instead of going through the switch, it started going through the capacitor only.
बट बीच में कनेक्टेड है ना जंक्शन तो how will it split like that?
Why does it matter? देखो ना, I is coming, I is going, I is coming, I is going. Node में current is zero.
हाँ ठीक है. Yes sir.
I am not creating any extra current there.
हाँ.
So the thing is, see, I am showing like an 8 shape. Maybe it is happening like this. These two currents are coming. This is going like this and this is going like this. क्या पता?
हाँ.
We cannot differentiate between the current. Anything could have happened.
Yes. Thank you sir.
No. So what happened to all this energy? This must have become heat. Make sense? And if you can clearly see here, 4R and R both have same current. So power in 4R is to power in R will be in the ratio of I square is to 4R is to I square R. 4 is to 1. That means whatever heat you're producing, so heat in 4R must be 4/5 of the total heat. Make sense? Since both have same current at any instant. Again, agreed. This current will keep changing, but this current is same in both. There I brought the circuit there. What are you asking? Where will the current go then? Now, Poroja.
No, but how do you know that it will split equally? 4R or R?
Where am I saying it is splitting equally?
नहीं
Does it look like it is
दोनों
splitting?
का
It is not splitting equally. Where it is splitting equally? It is the same. Just currents are just going.
नहीं आपने दोनों का आई दिया है.
Because it is the same current, na, right? Whatever current the inductor has, that only it will go through this, na.
हाँ yeah okay yes
Your the battery नहीं है यहाँ पे. No one is creating current out of nowhere.
right.
Inductors में whatever current is there, that only has to go somewhere. And both the inductors say, boss, we don't want to change the current, so both will try to drive the same current.
Yes sir. Thank you sir.
Clear with this? It's a pretty good one in steady states. You have a capacitor, inductor, and everything. You should definitely check it out. This is how they can play around. Clear? Take a small break. Come back by 9:43. We'll continue from here. Any doubt so far?
Sir, page 112 पे.
हाँ.
सर मुझे स्मॉल आर की पावर 5 आ रहा है. I don't know why.
Yeah. यहाँ पे तो आर स्क्वायर, यहाँ पे आर है, आर क्यूब डी आर।
तो 2 पाई RL पूरा है, चीज निकाल सकते हैं ना इसको।
क्या?
अच्छा है, मैंने कुछ गलती किया होगा, मैं बस चेक करता हूँ सर।
चेक करो, आई डोंट नो, देखो दिख रहे हैं ना, देखो समथिंग इज रॉन्ग, टेल मी व्हाट आई डिड रॉन्ग।
हाँ सर, करता हूँ, एक सेकंड।
चेक कर लो, आई कुड बी रॉन्ग बट यू हैव टू टेल मी व्हाट इज रॉन्ग। चलो कम बैक में 943। Next thing. Yeah, that's a little about the steady state. Next thing, LR charging circuits. So if you have an inductor, VLR, and let's say you close the switch at t is equal to 0. So after time t, let the current be I. Then you get the equation V minus L di by dt minus IR is equal to 0. This will be di by V minus IR is equal to dt by L. Integral on both sides, 0 to I, 0 to t. This will be minus 1 by R ln V minus IR by V is equal to V by L. So we get I is equal to V by R 1 minus e power minus RT by L. There. This is your current at time t. Same thing, we define something called time constant, which is tau, which is L by R. Quite useful for units and dimensions. They'll ask you, like, it was a CET or some question there. Find the dimensions of R by L. Most people try to find RL and then do it, but if you remember it's a time constant, you'll get it. The same definition, it's the time taken to decay the current by 63%. So if you plot I versus T graph, current will go from V by R here to 0. Sorry, here current is increasing. So this is the time taken for the current to increase by 63%. Play with this. This is the standard stuff. They can ask you something better. They can ask you, find the time when the rate of charging an inductor is maximum. Remember we did this in capacitors. Find the time when the rate of charging of capacitor is maximum. So as the inductor is getting charged, there is some point where it is getting maximum power. So if you take power in the inductor, so we have I is equal to V by R 1 e power minus RT by L. So if you have an inductor, current I, voltage across the inductor is L di by dt. They can ask you these kind of questions. So power in the inductor. So power is simply voltage into current. Remember, that is always true for any element. Power of a capacitor, power in a resistor. So I square R was a special case for a resistor. So power in an inductor is voltage in the inductor into current in the inductor. So voltage is L di by dt. Di by dt will be V by R, R by L e power minus RT by L. Current will be V by R into 1 e power minus RT by L. So we get power is equal to V square by R. E power minus RT by L minus E power minus 2RT by L. This is your power at time t, everyone. This itself is another question. What is the power in the inductor at time t? Now for this, if you try to do maximum minima, dp by dt equal to 0. You will get minus R by L minus E power RT by L plus. You will end up with T is equal to L by R ln 2. L by R is your time constant. So if you actually plot the power in an inductor versus time graph, so the inductor initially current was 0, so it will start charging, it will go to maximum, and then it will decay till infinity, it will take time. So this maximum occurs at L by R ln 2. If you remember this, we have done the same thing in RC circuits also. Yeah, this was a question. Power and the capacity. This was even more weird. Initially, it had some charge. So find the time when the power in the capacitor is maximum. We did the same thing. We did V into I, and then we differentiated it. So you can see a lot of similarities. It's not like, you're doing everything new. It is important, try to connect stuff to as many chapters as possible. That way, your understanding and how much you remember, it becomes easy. If you think everything is new, you will get overwhelmed. Clear with this. So charging may, I can even include the power thing also. So these are the main formulas here, time constant. Yeah. Next thing, LR discharging circuit. So unlike a capacitor, right, where you can charge it and keep it aside and then use it later, inductor, you can't do that. Because in an inductor, there is an energy as long as there is a current flowing. So if you take LR discharging circuit, so you have to first construct an charging circuit and then use it to discharge. So we have a battery, an inductor. So initially connect the switch to A, so it is charging, then you flip the switch to B. So when it is connected to A, it is charging. So the initial current will be V by R1. So once you flip the switch, so let the current be I. Apply Kirchhoff's law, minus LdI by dt minus IR is equal to 0. Integrate this, you'll end up with I is equal to V by R e power minus RT by L. Yeah, it's a straightforward LR discharging circuit. V by which R is? This is R2. So remember, the current depends on R1, but your decay constant will depend on R2. This is easy. There's nothing much there. So if you try to plot a graph, this will decay. In one time constant, you become 63% you will lose. Clear this? Yeah, so you know how to integrate this. If I give you something. So you guys remember the general solution? A plus B e power minus t by tau. So you can use the same stuff here. There's no difference between them. So let's see that. Any doubts on this thing so far? Any doubts? Great. Then let's see your general solution. So it is simply I is equal to A plus B e power minus t by tau. So how do we solve this? So same steps as this. Step one, let's find the time constant. How do you do that? Replace all the batteries with wires. Step two, find R equivalent across L. Step three, then your time constant will be L by R equivalent. Step two, find the current at T0. Then you get I is equal to A plus B e power 0, which is A plus B. Step three, find the current at infinity. This I taught you how to do in steady states. And this will be I infinity will be A plus B into e power minus infinity, which is A. There, three variables, three equations, you'll get everything. Clear with the process? It's the exact same thing we did in RC. Any doubts on the process? Yeah, let's see a question based on this, and then that should get you used to it. Now, see, the best thing about this, right? This is not current in the inductor. That I can be current in any branch. This is an example which we did one of the problem here at T0. I want current in this branch. Find I at time t. So that is the best thing about this general solution, right? It need not be current in the inductor. That I can be current in anywhere in the circuit, and it still works. Let's get that. Find the current in the 2R at time t. Remember the process. Finding the time constant, find the current at T0 and current at infinity. You already know this step 2 and step 3. Try. You got 3-4 minutes. Question. This is the question, right? Ahana. What are you asking? You're asking for the steps. Hmm. Let's see how to do. पहले भेजा था तब अपने मेथड का स्लाइड. Which one you're talking about? I'm confused. ठीक है, let's see. Are you asking about the steady state? Yeah, T0 and that one. This one.
अरे नहीं सर, वो पहले भेजा था जब आपने मेथड का स्लाइड रखा था, लाइक क्वेश्चन देखना था तभी.
Okay, yeah, you sent it long back. मैंने message skip हो गया.
यस सर.
ठीक है. See, now what is the first thing? Finding time constant. What to do? Make all the batteries into wires. This is R, this is 2R, this is R. So you want to find R equivalent across this. R and 2R parallel. That is 2R by 3 plus R. So R equivalent 5R by 3. Time constant L by R equivalent 3L by 5R. Yeah. And what about the currents that we have done here? There. I know the current at T0, I know the current at infinity. You got everything. Then your general solution. I is equal to A plus B into e power minus t by tau. Tau is 3L by 5R. So T0, your current was V by 3R. This was A plus B. At T infinity, current was V by 5R, which was A plus 0. So from here we'll get B is equal to 2V by 15R. Therefore, the current I will be V by 3R plus 2V by 15R e power minus t by tau. So 5RT by 3L. Check. Got the steps, everyone? You already know how to do T0. You know how to do a T infinity, steady state and that. You know how to find time constant. Clear? Let's see one more like this. Now you guys try. I'll keep them together. This is R, this is V, this is 2R, this is R, this is L, this is 2V, and the switch is this. This is the current I want you to find. Find I at time t. And find the net current and then split it in the ratio of 2:2. No, you can't do that, Furoja, because both the resistors are not in parallel. Na? There's an inductor sitting there. And net current भी कैसे निकालोगे? There is no R equivalent there. If the L is sitting there, how are you even taking them as parallel? Find the time constant, find the current at T0, find the current at infinity. If you got these three, you're done. Infinity current won't be easy, it won't be straightforward. That itself is another problem. Try, 2 minutes more. Let's see. So let's find the time constant. Others keep trying. Nice. You still have time by the time I finish it off. This is R. This is 2R. This is R. This are in parallel. R by 2. R equivalent will be 5R by 2. Tau will be 12 by 5R. At T0, inductor won't work only. So all the current just goes here. V by 2R. Hope till here everyone must have got it. Now at T infinity, this itself is a proper mains level question. The circuit will look like this. Some people will think we can use V equivalent and do it. Not a bad idea, but the problem when you take V equivalent, this will become one battery. You will get current in this branch. But the question, you want current in this branch. So you can go with Kirchhoff's loop law or you can go with the junction law. I'll take this as 0, 0, 0. This is V, this is 2V. Let this be X, then this is also X, this is also X. Let the current be I1, that's what I'm trying to find. Let this current be I2 and let this current be I3. The total current entering the junction must be 0. I1 plus I2 plus I3. So I'll take V is greater, so V minus X by R, 2V minus X by 2R, 0 minus X by R is equal to 0. R goes off. V 2v minus x 5x by 2. X is equal to 4v by 5. Therefore, I1 will be v by 5r. Am I right? Looks right. That's your I1. In case you don't like this, you want to use Kirchhoff's loop law. I actually have one more idea. I will tell you that. Let's see. So let's take this current as I. This will be small I, and this will be I minus I. Take this loop and this loop. V minus IR minus I into 2R minus 2V is equal to 0. The other loop will be 2V plus I into 2R minus I minus I into R is equal to 0. From here, you have to find I. You will get I somehow. The other idea is this. Again, it depends on examiner what clicks. Generally, for me, the first thing, the Kirchhoff loop law clicks for some reason. It's not even the junction law. It doesn't matter. Examiner don't think so much. If maximum there'll be a difference of 1 minute, just finish it off. Here, what I would suggest, assume there is a battery of 0 volt. Treat this as one battery. Then what will be the equivalent battery? 2 into R plus 0 into 2R by 2R plus R na 3R. Even R1 plus E2 R1 by R1 plus R2. That will be 2, 3 volt. R equivalent will be 2R by 3. So now your circuit becomes like this. Just two batteries. This is V, this is R, this is 2R by 3, and this is 2V by 3. So now you want to find the current in this. I will be V minus 2V by 3, and resistance will be 5R by 3. This will be V by 5R. This thing, so just now I thought about it. There, that also works. So you see what clicks. So if you don't have a battery, I can take it as a 0 volt battery and do it. Why does Max care about it, right? Max doesn't show partiality between any numbers. I'll take a 0 volt battery. Got this? So there I got everything. Now let's solve. I is equal to A plus B minus E power minus T by tau. Tau is equal to 12 by 5R. At T0 current I will be V by 2R. At T infinity current is V by 5R. So B will be 3V by 10R. Therefore, current will be V by 2R plus 3V by 10R e power minus 5RT by 12. Check. Clear with the steps. The biggest headache is finding the current at infinity. Clear? Yeah, that's a bit about RC circuits, like RL circuits. So I give anything, you can figure it out. There are more varieties on, we will see later on also, LC and everything. Let's see one more. This is a good one. It's a nice theoretical one. Let's say we have an inductor and a resistor and a battery with a switch. And here you connected an ideal voltmeter. So the question is, what will be the reading of this voltmeter? Case 1, at t is equal to 0, just after switch is closed. If you just close the switch, what will the voltmeter show the reading as? After long time, if you close the switch for a long time, then what will be the reading of the voltmeter? Switch is closed for a long time and then you suddenly open. Then what will be the reading of the voltmeter? Three cases. What do you guys think? Let's see. In the first case, you know what happens? At t is 0, there is no current. The inductor will not let any current flow. So you can see the voltage of the battery will be voltage of the resistance plus voltage of the inductor. And voltage of the inductor will be I into R, and this is 0. Therefore, this will read only V. So all the voltage will be across this thing only, the inductance. Isn't it? If there is no current in the circuit, the resistor will not have any voltage. So all the voltage has gone to the inductor only. It has absorbed all the voltage, but it is not giving any current. If you leave for long time, t infinity, your inductor simply becomes a wire. Now, if you take a voltmeter and put it here, it is going to show 0. Mathematically, you want to prove, eventually the current becomes V by R, which is constant. And voltage across the inductor is nothing but L di by dt, and di by dt is 0. And something interesting happens with the third one. In the third one, after a long time, the current has become V by R. Now you open the switch suddenly. Current becomes suddenly 0. So your VL becomes L di by dt this value will tend to infinity since dt tends to 0. So you will get the reading, the voltage across the inductor will become much, much greater than V. So the reading will be much, much greater than the voltage. You can put a 10 volt battery and generate 10,000 volts. Now, how much will generate that we don't know, but you get a pretty high voltage, right? And now what happens if you have a very high voltage? Now this will be the high voltage across the switch. So due to the high voltage across the switch. So if you have high voltage, you also have high electric field because potential difference by distance is the field. Due to the high voltage across the switch, there is a high electric field. And anyone remembers what happens if you have a high electric field? Electrostatics. याद है रशियन हैकर का वीडियो? Dielectric breakdown. Charge will leak. There is a high electric field resulting in dielectric breakdown. Air becomes conducting. So the charges will start jumping across the switch. That's what we call as sparks. So this is actually a pretty interesting source to generate sparks. Did you ever think about this? How does your, when you're starting your Activa, that electric ignition, which you get that sound, karke, how does that start actually? So what happens is in your engine, right? You have an atomizer which injects the fuel. So the fuel is pretty much spread out. So you need some kind of spark to ignite this. So when you press that, what you're doing is indirectly, you're charging an inductor and you're opening the switch. You get sparks. You use that sparks to ignite the fuel. A pretty efficient way to generate sparks. And not only this thing, if you have seen this, this old tube lights. Ever seen this tube lights? You must have seen this thing. This is called a starter. These are called starters. Not your eating wala starter, but so the thing is, this tube lights, right? Again, these are 10-15 years old tech, old one. So inside you have a small mercury drop and some gases, inert gases. So in order for the air to become conducting, you need a high voltage. You need around 10,000 volts to start that tube light. It's actually a mini cathode ray beam inside, kind of like that. Getting it? Now the problem is your house ka voltage is only 220. So what this starter does, it takes the voltage, it charges an inductor and discharges instantaneously, generating high voltage. Once the air inside becomes conducting, you need only low voltage to maintain the current. It's like your activation energy. Once you reach activation energy, after that you need less energy to maintain the process. So you need the starter. So once you keep the starter, once the tube light is on, you can remove the starter. It still keeps glowing. So inside this, right, the air becomes, the current will start passing through the air. So these molecules will gain energy. They start colliding with each other and they emit X-rays. Electrons go to higher orbit. When they come down, they emit X-rays. These X-rays fall on this white color powder, which actually has a phosphorus ka compound. And the phosphorus absorbs this ultraviolet and then electrons get excited and again de-excite, emitting visible light. So if you actually remove that white color powder and if you switch on the tube light, it is glowing, but it is emitting ultraviolet. The room will be dark. You can't see, but it is very bright. It's not in your visible region. So that is the thing. Let me try to show you something. I'm pretty sure it will lag a lot, but let's see.
demos towards small areas, which means that the energy flowing feels the flow, but it's still really fast. A huge is from turning off the current. This who killed your joy. These demos. Side note: pyrotechnics is sometimes a side wire laid over the.
There. You can see that orange stuff here. That is an inductor. It's a very high voltage inductor there. Inside you have a lot of coils. If you are ever studying, you know this thing, what do you call it? High voltage department in IIT Madras, they have a high voltage separate section. You can generate voltage up to 1,50,000 volts or higher. You can actually literally get sparks and everything. So we actually use inductors for this. It's a pretty big one.
When you flip the switch to allow
Now look at the switch. This is that old typical tick switch. You know, you must have seen this. If you ever have that switch, whenever you switch on, switch off, you get sparks. So look at this switch. It's a
electricity
big
to run
one.
through the
Now
coils,
see, when you close the switch, nothing
the
happens.
wire on top jumps off. Meh, it's kind of wondrous. With
Even
another
also that
wire
when you
limits
close
a
the
side
switch, nothing
effect at
happens.
top. The really counted. It's really just because of the magnetic fields produced by the currents that push them apart. But learning. Now, when we turn off the current, things get real saucy. Okay, that jumped
Saucy.
off, and then. Oh my gosh!
Look at that in the slow motion. Can you see? You don't have a problem when you're closing the switch. But the moment when you try to open the switch, you can see the sparks, you know, they're getting generated between the openings. Technically, the wire is not connected, but through the air, the charge is passing. You can see the sparks, how bright it is. Circuit got disconnected. So the thing is, this happens every time in your house. Did you see a typical Bollywood ka plot when movie ka plot hota hai? You know, the gas is leaking in the kitchen. The heroine accidentally goes into the kitchen and switches on, and there's a blast. If you have seen that, that's a typical plot, right? So actually, there's a wrong mistake with that. If the gas is leaking, when you go into the kitchen and switch it on, nothing happens. When you switch off, that's when the blast happens. You get a spark every time you switch it off. The reason you don't see it is because of the plastic covering is there that hides it. So this is an electric kettle. Again, some of you can see, some of you can't see. So there will be a thing. Anyway, I'll post the videos in the group. Let's see if you can see a spark. So you can try this at home also. Put an electric kettle. Actually, if you remove that white color plastic, you can clearly see a spark. So this guy puts a spark. This thing, now see, switch on, switch off. It is on. Because a kettle, right, has a heating coil. It's a very good inductor.
Oh.
Now, see if you can see the spark. When you switch on, nothing happens. When you switch off, did you see the spark? It just comes in one frame. I think it just skips when there's a lag. Let's try that again. Let's see. I'll try to. Now it comes. It should come now. Now did you see? Dekha na spark aage. That's what happens. When you switch on, nothing happens. Every time you switch off, there's a spark. Hope everyone got to see that. In case you didn't see, I'll post it. You can check it out. So this happens every time in the house. So there, that is the thing. Okay. So there, that would be the last one for that. I will wrap up with that. I'm done actually. I'm also pretty decently enough. I think I've pulled it till 2:30 and that. Okay, with that we'll wrap up with that. So we'll catch up on Monday. We'll continue from here. After this, we are left out with, we'll do few more questions on this. And then we'll do something called LC oscillations. What happens if you put an inductor and a capacitor together? And then we will see something called mutual inductance. I think next class, we will wrap up almost most of it will be done. I think by next Friday, we will wrap up the chapter and we'll start off with alternating current. So yeah, so you can start doing it. Don't delay anymore. In case you're solving your HCV or